Have you ever seen digital audio specs like 16-bit, 24-bit, 44.1 kHz, or 48 kHz and wondered what it all means? What is bit depth and sample rate? How do we translate continuous analog sound waves to digital ones and zeros? And how does a computer make sense of a sound? In this video, we will figure that out and touch upon key concepts you need to know to understand how digital audio works. First off, what exactly is sound? At its core, sound is vibration. When an object vibrates, it creates pressure waves that travel through a medium like air, water, or even solids. These vibrations are what our ears perceive as sound. Imagine a plucked guitar string. It vibrates back and forth, creating these pressure waves. These waves move particles in the air, and these changes in air pressure reach our ears. These waves have properties. Frequency, which determines pitch. Higher frequency means higher pitch, like a flute, while lower frequency means lower pitch, like a bassoon. Amplitude, which determines volume, how loud the sound is. The bigger the amplitude, the louder the sound. And wavelength, which is just how long the full wave cycle is. So how do we turn this continuously varying signal into numbers and back again? That's where converters come into play. Analog to digital converter, ADC, converts the incoming continuously varying analog signal into a stream of digits. Conversely, to turn those digital files back into sound waves our ears can hear, we need a digital to analog converter, DAC. Its job is to reconstruct an analog signal from ones and zeros. Now, how exactly do we capture analog sound waves and turn them into something a computer can understand? That is, zeros and ones. What's the logic there? Well, here's how analog to digital converters work. The first key concept is sampling. Think of it as taking snapshots of the sound wave at regular intervals. We are measuring the amplitude of the wave at that point in time. Samples are taken at precise, regular intervals. During each snapshot, the amplitude or height of the signal at that exact moment in time is measured and immediately stored as a number with a defined resolution. The frequency at which we take these snapshots is called the sample rate, measured in hertz. Think of sample rate as the speed at which we sample the wave. It dictates how many times per second we capture its amplitude level. If the sample rate is high enough, we can accurately represent the sound wave. Again, the number of samples taken per second is called sample rate, and it's expressed in kilohertz. Common sample rates include 44.1 kHz, meaning we take 44,100 samples every second. This is the CD standard. 48 kHz, common standard, often used for audio and video. Higher rates are used as well, like 88.2 kHz, 96 kHz, and even 192 kHz for high-definition audio. Next, we have bit depth. This determines the amplitude resolution available for each sample, or how accurately we can measure the amplitude at each sample. Think of it as the number of steps available on a volume scale. A higher bit depth means a wider range of those steps, allowing us to capture smoother transitions from the quietest whisper to the loudest explosion, while simultaneously providing more headroom in the recording. In digital audio, bit depth is the number of bits, the fundamental ones and zeros used to describe the possible values for each snapshot of the sound wave. To understand this better, we need to understand the basics of binary. Computers work with binary, a system where information is represented using only two digits, 0 and 1. Each digit is called a bit. A 16-bit word size means we have 16 slots for those zeros and ones. Each combination of zeros and ones represents a unique number, and since there are two possible values, 0 and 1, for each of the 16 slots, the total number of possible combinations is 2 to the power of 16, or 65,536. These combinations are those steps available on our volume scale. Imagine 65,536 of these red lines that represent unique values that map the range from complete silence to the loudest possible sound our 16-bit system can handle. Similarly, a 24-bit depth has 2 to the power of 24, or 16,777,216 possible combinations, resulting in a much wider range of amplitude levels. So what does a low bit depth, like 3 bits, actually mean for our sound? Well, 3 bits gives us 2 to the power of 3, which is just 8 different possible values. That means our entire amplitude scale, from silence to the loudest possible sound, gets divided into only 8 steps. Imagine trying to measure someone's height with a ruler that only has 8 markings. You'd have to round quite a bit. It's the same here. The system rounds the actual amplitude to the nearest of those 8 steps. This lack of detail means we lose nuances and can't accurately represent the full dynamic range. That's why we normally use much higher bit depths. Here are some common standards. 16-bit, the classic CD standard, sufficient for many forms of playback. 24-bit, the standard in most modern DAWs and lossless audio files, providing excellent dynamic range. 32-bit, considered high-resolution audio, used for recording and mastering. Let's lay down sample rate and bit depth on this graph. Here's our sample rate. Again, it's how fast we take samples. Now those samples need a value, amplitude, which is how loud the signal is at a specific point in time. We end up with this grid, which can be looked at as audio resolution. The faster we take samples and the more possible amplitude values we have available, the more precise digital representation of the sound. Bit depth directly impacts a digital audio system's dynamic range. That is the difference between the quietest and the loudest sounds that the system can handle without distortion. Higher dynamic range enables us to capture everything from delicate whispers to a full orchestra at its peak. Each additional bit adds approximately 6 decibels of dynamic range. For example, a CD with its 16-bit format has a dynamic range of 96 decibels. This is sufficient for most music, but modern DAWs often use 24-bit audio for a reason. That wider 144 decibel dynamic range provides greater flexibility, allowing engineers to capture soft details along with powerful crescendos, all with increased headroom to prevent distortion during recording and editing. Finally, we need to touch upon pulse code modulation, or PCM. It's the standard and most common method for representing audio in digital form, and it's the method we covered in this video. Popular file formats like WAV and AIFF use PCM encoding. An interesting alternative, though less common, is pulse density modulation, PDM, which represents amplitude by changes in the density of pulses rather than the magnitude. And that's a wrap. I hope this video has given you a solid understanding of the basics of digital audio. Keep in mind, there is much more to digital audio. We didn't talk about things like the Nyquist frequency, aliasing, or dithering. If you're interested in learning more, check out the blog post linked in the description below. And if you learned something, please click subscribe and like the video. Thanks for watching.